here is a practice problem, and I'm going to do this problem and I'm going to lead it into something much better. So let's just get started. So the problem, I made up this problem and I drew it on graph paper. Look at that. The problem says, I'm saying the problem because I didn't write it down. The problem says that there's a puck at position 1, R1 at time 1.2 seconds, and here's the value, and I actually measured it, to 5.50. I'm going to confine this to the XY plane, where Z is this way, just to make things easier. And then a little bit later, at time 1.8 seconds, it's at a position 530, and we call that R2. And so the question is, where is the puck going to be at time 1.9 seconds? So what we want to do is to use our definition of average velocity. If I can find the average velocity going from here to there, I can use that to project where it's going to be a little bit later. And you could kind of already think about this, right? If it's going from here to there, let's just draw a little dotted line. It should keep moving in the same direction if it has a constant velocity. In this case, I didn't say that, but it does. So here's the direction. It should be somewhere on that line, but where on that line? There's a lot of ways to do this, but let's do this the physics way. Okay, I'm going to actually, what I want to do, I'm going to show you graphically what we're going to do, and then we're going to do it on a different sheet of paper. So the first thing we're going to do is to calculate this vector, the displacement, delta r, which is this vector minus that vector. After I do that, I'm going to calculate the average velocity, V average, which is delta r over delta t. Once I do that, I can use this average velocity with my new delta t. This delta t is going to be, I'll write this out. This is going to be r2 minus r1. That's the displacement over t2 minus t1. Once I have that average velocity, I can say, well, that same average velocity is going from R3 or R2 to R3, T3 minus T2, right? I can do it going from here to there. And then once I do that, I can solve for this R3 since I already know this V average. I know R2. I know all the times. Let's get to it. It should be somewhere over here. Let's get to it. Okay, switching to actual paper. Did I not get enough paper? There's paper. Okay. No, that's not enough. Okay, if I need more paper, I'll get more paper. So let me just rewrite my vectors. I have R1 is, I already forgot. I'll put it right here. R1 is the vector 2, 5.50 meters. R2 is the vector 5, 3, 0 meters. T1 is 1.2 seconds. T2 is 1.8 seconds. So the first thing I want to find is delta R. I want to find the displacement going from 1 to 2. That's just going to be R2 minus R1. And so here I can say, if I want to subtract vectors, if I want to subtract R1 from R2, I subtract their components. So this is going to be, the x component's going to be 5 minus 2, which is 3. This is going to be 3 minus 5.5, which is going to be negative 2.5. And then 0 minus 0 is 0 meters. I also need delta t. Let's write that. Delta t is going to be t2 minus t1. That's going to be 1.8 minus 1.2 equals 0.6 seconds. I'm going to actually calculate this on my calculator. There it is. My dumb old calculator. Okay. So now I can calculate the average velocity, delta r, over delta t. That's going to be this, delta r, 3, negative 2.5, 0 meters divided by 0.6 seconds. So how do you divide a vector by a scalar? Well, you divide each component by that. And I'm going to do this in the calculator just so I don't make a mistake. So I'm going to take 3 divided by 0.6. So you can see right here, I want to not get it in the lights. So 3 divided by 0.6. That's I knew that one, 5. Then I have negative 2.5 divided by 0.6. 4.17. Let's say negative 4.17. And then this one I can do without a calculator. It's 0 divided by 0.6 is 0. And that's going to be, each one of these is meters divided by seconds. This is meters per second. And that is our average velocity. Okay, so now I want to find out R3. I want to find the position at R3 where T3 is 1.9 seconds. So just a tenth of a second after that. So let's again start with our same average velocity formula. V average is delta R over delta T. But if it's average velocity, then I can use any R's and T's as long as the R's go along with the T's. So let's do this. R3 minus R2 over T3 minus T2. I know everything here. I know V average, I know R2, I know T3, I know T2. The only thing I don't know is R3. So let's multiply both sides by T3 minus T2, and I'll write it over here, R3 minus R2 equals V average times T3 minus T2, which is just a scalar. And then I can add, that's a vector. I can add R2 to both sides, and I get R3 equals R2 plus V average times T3 minus T2. Now let's just go ahead and put in all our vectors. So R2 is this vector. It's going to be 5, 3, 0. I'm going to leave off the units for space, and then I'm going to say plus the average velocity, which I just calculated right there, 5, negative 4.17, 0, times T3 is 0.19, T2 is 1.8, so this is going to be 0.1. So let's rewrite this. I'm running out of a little space. I don't want to get a new sheet. Let's rewrite this as 5, 3, 0, and then I'm going to multiply each of these by 0.1. I don't even need a calculator to do that because it's just multiplying by 0.1. So this is going to be 0.5, negative 0.417, 0. Now I can add those together. I can add those two vectors. 5 plus 0.5 is 5.5. 3 plus negative 4.17 is going to be 2.583. Is that right? I hope I didn't make a mistake there. I did it in my head. And then I can do this one, 0 plus 0 is 0. And that's where it's going to be. That's R3. That's the position it's going to be. Let's just go ahead and put that on the paper right here. I'm going to write here, R3 is 5.5, 2.583, 0 meters. So let's see if we can mark that. So 5.5 is along this line. 2.583, so here's 2.5. It should be a little bit higher than that, so about right there. That's where it should be. And it's on that line, so that's kind of cool. Okay, I'm not finished. So now let's just redo this problem. And I actually want to do one thing. I want to show this. I want to show that I could find V average as delta R over delta T as R3 minus R1 over T3 minus T1, and still I get the same answer. I'm going to do this calculation in Python though, because I want to do something very cool to show you. So let's do that. Okay, I'm switching over here to Python. Here we are. So I'm using GlowScript WebV Python. This is in trinket.io. There's also glowscript.org. You can use this. It's online Python. I'll give you the link to this code, and you can change it if you want or not change it. Doesn't really matter. So I'm going to do this the very easy way, and then we're going to make something awesome. Okay, so let's start off with everything that we know. I'm going to write down R1 as vector. What did I have? 2, 5.5. I'm going to put everything we know, 0. And I'm just going to print that just in case you don't remember how this works. Print R1. So if I run that, I get the vector. So vector is a reserved class in GlowScript, and it actually treats these as vectors, which is super nice. R2 is vector, and it was 5, 3, 0. And then I had T1 was 1.2, T2 was 1.8, T3 was 1.9. So let's first just calculate the average velocity. So I'm going to say dr is r2 minus r1. So you can do that. I can make a new variable, and I can call it the difference between two vectors, and that's fine. As long as it's a legitimate vector operation, it'll be fine. I'm going to say dt is equal to t2 minus t1. I'm redoing the first calculation I did, and then v average, I'm just going to call it v, is dr divided by dt. Let's print that. V equals v, and let's put the units meters per second. And if I run that, it gives me the average velocity. And you see it's the same thing that we got before, which that's not a surprise. Okay, so now I want to find R3 based on R1. So let's do this. I'm going to use, if I use the same algebraic formula, I can say R3 is equal to R1 plus V average times dt, but dt would be T3 minus T1. And let's say print R3 equals R3 meters, and run that. We should get the same answer, and that's the same answer. Okay. Now, but what if I want to find it for the next? I want to find it at R4. Let's just do that. What if I want to find R4, and that's going to be equal to, let's just go back. Let me say R after another 0.1 seconds. So I'm going to say R4 is R3 plus, I'm going to go over here and say dt is 0.1. I'm going to just want to do 1/10 of a second step interval all the time. I can go back here to v times dt. That's it. I can find the new R4 just by taking the previous R and my new time step and my average velocity, and I can find that. And then I could do R5. R5 is equal to R4 plus v times dt. Let's print both of those just so we can see that it actually is working. Print R4 equals R4 meters. Print R5 equals R5 meters. Run it. So it's moving forward in time. So every time interval of 0.1 seconds, I can recalculate the new velocity. And I could keep doing this as much as I want. And this is the beauty of Python. We're actually going to make it more complicated later, but I can keep moving this thing forever with the same idea. So let me show you how this works. Let's go back up to this code and let's just totally change everything. I do want to calculate this average velocity, but after that, I'm done. I want to get rid of this stuff. So now what I want to do is to say this. Let's say t equals, I want to be at, I just did 1.8, so I'm going to say 1.8. I haven't done this T3 yet, so I'm just going to delete that. And dt equals 0.1. Now I want to calculate the position up to, let's say, t equals 3. So I'm going to say this loop. I'm going to show you how it works. This is, now we're getting into programming here. While t is less than 3, I'm going to print t. Let's just print it. T equals t, comma, seconds. And then I'm going to say t equals t plus dt. So this is a really important statement in Python and one that you have to really be careful about. This says take the value of t right here, which is starts off at 1.8, add dt, which is 0.1, and then make that the new value of t. So we can do this in Python to change the value of a variable and not have to rename it. I don't have to worry about t1, t2, t3, t4, t5, all that. I'm just going to call it t. And this statement does work. Now, it's not an algebraic statement. Okay, these t's don't cancel. This t and this t doesn't cancel because That's not an equal sign. That's not an algebraic equal sign. This right here is a make equal to sign. In Python, this says make it equal to. Okay, so let's just run this and see what happens, and then maybe we can understand that. So you see what it did. It started with the first time of 0.1, 1.8, 1.9, 2, 2.1, so it all went all the way up to 2.9. It didn't get to 3, right? It did get to 3, but I printed the time before I updated it. If I want, I could change this. This doesn't really matter too much, but you can play around with these while loops. We're just going to make it simple. It shouldn't matter too much. This one will get to t because it'll update t to 3, and then it'll print it, and then it'll go up here. Before I printed it, then updated it. So this one will go, but you'll notice here it starts at 1.9, and then 2. It doesn't really matter. It's not a big deal, trust me. I don't even need to print that. Okay, so now what I want to do in this loop is to update r. So I'm actually going to come up here and say r is equal to the vector 5, 3, 0. That's where it ended at r2. I don't want to call it r2 or r3 or anything. I just want to call it r. It's the one I'm going to change. Yeah. So now let's just update that the same way we updated time. I'm going to say r equals r plus v times dt. And we can get rid of this right there. And then I'm going to print it. Print, let's do this. R equals r meters at t equals t seconds. And then we're going to get a bunch of stuff. And that's a lot of data right there. And it's nice, right? It gives us a whole bunch of, I know at time 1.9 seconds, that's where it's at. At time 2.2 seconds, here's the location, right? So it's great. It's just kind of messy. And you can imagine I could even make a smaller time step. I could run it for a longer time. But what I want to do, I don't like this data. I want to make a graph instead. So let's make a graph of the x position as a function of time. That's all I want. So graphing in Python is not too terribly difficult. Up here, I'm going to put one line. I'm going to call it g1 equals graph. Now I can give it a whole bunch of parameters, which I'll add later, but right now I'm not going to. And I need a plot. I'm going to call this fx for my x function. And it's going to be a type called, let's do g-curve. There is g-dots too, and I'll show you. And so those are functions. Graph is a function built in. G-curve is a function. I didn't give it any parameters though. I just passed an empty function. And we'll fix that in just a second. So down here, to make a plot, all I need to do is, I don't want to print, I'm going to comment that out. I'm going to say fx.plot, and I want to give it what's my x coordinate, what's my y coordinate on the graph. So my x coordinate I want to plot is time. So I'm going to say t, and my y coordinate I want to plot as the x position. So I can't plot r because that's a vector. That's got 3 pieces of information. I only want one piece, and that's the x value. So I can get that as r.x. r.x is going to be the x component of that vector. So let's see what happens here. And there you go. So this is actually a finite set of data points, but this is the x velocity, x position as a function of time, constant velocity, which would be a constant slope. Let's make the graph prettier. So I'm going to give it some things like this. Title equals puck motion. I don't know. You can call it whatever you want. X title, I'm going to call, you got to spell it correctly. X title equals time in seconds. Y title equals X in meters. And then I'm going to, you can press return right there after you put a comma. I'm going to say width equals 400, height equals 200. So this tells me parameters of the graph, the axes, right? And I'm going to set this to 400 pixels wide because I'm kind of zoomed in on my screen here, and that way I can see the whole thing. And 200 high. Now for the fx, you can put things in here too. I can put things like color equals color.blue. I could do, was it dots? Or dot equals true? I can't remember. Let's try dot equals true. And I'm going to run it. Okay, so that leaves 1 dots. I think it's marker marker equals true. Let's try that. No, that's not good. Okay, there is a way to do it. Don't worry about it. Okay, let's just leave it like that. So you see we get a very nice graph. It looks, this is like, you could use this in a lab report or something. So this has the velocity, the position increasing right there. Let's actually go ahead and graph the y velocity on the same graph. We could make a separate graph, but let's make a y graph too. So I'm going to say x comma y. Now I need another function here. I'm going to call it fy equals g curve color equals color dot red, so it looks different. Down here, I'm going to plot fy dot plot tr dot y. And now I'm going to run that. And there's my x position as a function of time, my y position as a function of time, and everything is awesome. Okay, so this is a really important thing that we're doing here, breaking this problem into small time steps, which we don't actually have to do, but breaking it into small time steps allows us to do some important things later. So this is what's called a numerical calculation, because we're breaking into small time steps and calculating things along that path. Now, in this case, it doesn't matter how big your time step is, it's still going to work. Later, we're going to make some assumptions about these time steps where the size of the time step does matter. But we'll get to that. I just really wanted to show you the idea of using Python to calculate stuff and using a loop, and that's really important right there. Graphs are really important too. So we're going to use this for later stuff. I will give you a link to this code, but I think it'd be better if you just kind of follow along and type it, because you're going to make some mistakes, and the making mistakes is an important part of learning the process. If you just copy the code and paste it, you may not learn as much. But okay.